Hey, also we're going to go through a little bit more with series and parallel circuits. These are just very simple series and parallel circuits. We'll start with a quick review of what we've learned so far and maybe see if we can summarize, condense it a little bit, synthesize. We'll also go through a little bit more with parallel. We were kind of rushed a little bit at the end of class, so we'll make sure that we get to talk a little bit more about what's happening in a parallel circuit. And then we'll go through a few examples just to make sure that we understand what we're hoping to be able to accomplish here and how different circuits might look and how we'll be able to kind of put those together. All right, so here we go. The first thing I want us to do is just again look at these ideas of the series circuit and the parallel circuit. Now these are the simplest series and parallel that there can be. Now of course you can have other circuits that are a combination. For example, this one right here has two that are in parallel right here, but then those are in series with this one. So it goes through this, then it has to go through that combination there. So there's some different things that we can do here, different combinations, but right now we just kind of want to be able to get the basic idea and make sure we understand what's happening so that we can work through some more problems later. Okay, so in a series circuit, all right, so that's what we got right here. In a series circuit, we're going to talk about the potential difference, the current, and the resistance. Now, one of the things that we talked about in this series circuit is that we have a certain amount of EMF, a certain amount of potential that's being provided by the cell or the battery, the power source. As we go through, we said we are not losing any potential in the wire, but as we go through the resistors, we have a certain amount of potential difference. So I'm just going to say that this is delta V1 because this is resistor 1 and delta V2. So we lose a certain amount of potential here, we lose a certain amount of potential there, and then we go back to the beginning. That should be equal to the total potential or the EMF that's being provided by our battery, by our cell, by our power source. So here we'll say that when we look at the potential difference, we will say that the potential difference of the first resistor plus the potential difference of the second resistor must add together to give us the potential that's being provided here. And a student asked me at the end of class, he said, well, does it have to be equal? Well, yes, because the power being provided to your circuit has to be equal to the power being used in the circuit. Or in other words, the potential being provided has to be equal to the potential that's being used, right? There's no leftover in the end. We're using all of that potential difference throughout the circuit. So now we're going to look at the current. Now we talked about this in class as well. We said that we have a certain amount of current coming out of the battery that's going through the circuit. That same amount of current has to go through 1 and it has to go through 2, right? So in this sense, the current going through the first resistor has to be the same as the current going through the second resistor because it all has to go through there. You don't use up the current. And that has to be equal to the total current of the circuit, right? All of those have to be the same for a series circuit, all right? Then we move on to the resistance. Now the resistance, remember we said if we have two separate resistors in series, it's just the same as if we put them together. And so resistance, we're going to say this, that the resistance of the first resistor plus the resistance of the second resistor must equal the total resistance of the circuit, assuming that there's no resistance in the battery or in the wire. The no resistance in the wire is a fairly good assumption. It's usually very, very small. No resistance in the battery. We're going to talk about that probably next class. All right? So that's what we got here. Now let's go ahead and do the same thing for the parallel circuit, right? So when we're looking at the parallel circuit, what we talked about is that the potential difference provided here, right? We said if this was a 5-volt battery, that this would be 5, 5, 5, 5, 5. We'd have the same potential. Anywhere where the wire is connected, that should all be the same potential. So if my potential here is 5, then my potential there will also be 5. Potential doesn't split. Okay, potential is that level of energy kind of, we'll talk more about what exactly potential is next year when we do fields. But for now, just understand that the potential in a wire is the same everywhere. No potential is lost as long as it's connected. The potential doesn't split. It's all the same. which means exactly the same thing on the other side. If this is 0 because it's a 5 volt battery, 5 volts of potential, then everything along here will also be 0. That will be 0, that will be 0, and so therefore the potential difference across each of my resistors will be equal to the potential difference being provided by the cell. So again, I'm going to label this 1 and this 2. So what this means is that the potential difference in the first resistor will be equal to the potential difference in the second resistor, which is equal to the potential difference or the EMF being provided by the battery. Now, of course, this changes in a more complex circuit, but for this simple one, we can see that as long as the wires are connected, those both have to have the same potential difference. All right? Now, sometimes we don't put, I'm putting the little delta there. That's a habit of mine. You actually, for IB, we don't always have to do that. Sometimes we just put the V to say V is the potential difference across this resistor. All right? Current, though. See, current is a little bit more interesting now because the current is going to leave the battery. Current is the electrons, right? It's the number of electrons per second. So when the current gets here, the electrons have to choose whether they're going to go through number 1 or whether they're going to go through number 2. So the electrons are going to split up, and then eventually they're going to come back together again. Now the result of this is that the current that goes through the first resistor plus the current that goes through the second resistor, those will add up when they come back together to give me the total current in the circuit. All right? So 1 plus 2 equals 3. And remember, that's just conservation of charge. That's just making sure that we have the same number of electrons here as we do when they come together. That should kind of make sense. Now, the resistance is a tricky one. And if you want a proof for this, you can look in textbooks, you can look online. My job right now is not to give you a proof. It's just to give you the mathematical tool that you need to be able to solve a problem like this. Okay? And so therefore, one thing that you'll notice is that as the current goes through and as it splits up, you now have less current that's trying to go through those resistors. Now what that means is that this will have less resistance than if I forced all the electrons to go through both of those. Putting things in parallel means that there will be a smaller total resistance. Now the mathematical way to do this, which we won't prove right now, is to do 1 over the resistance of 1 plus 1 over the resistance of 2. So resistance of 1, resistance of 2 is equal to 1 over the total resistance, just like that. Okay? Now, you may wonder, well, how exactly does that work in context with the question? Well, that's what we're going to do now. Okay? So we've talked about how these connect: potential difference, current, resistance for series and for parallel. We've tried to kind of reason through how that makes sense, but now we're just going to work through a couple of problems. Okay? If you're in my class, this is example number 11 and number 12. We'll look at number 13 in just a minute. But we'll go ahead and start with these. So when I look at this circuit, I see very clearly right here that these two are in parallel, right? The current splits, it goes through either one or the other, and then it comes back together. So what I'm going to do is I'm going to take those two and I'm going to combine them into one effective resistance. Okay, that's using this right here because that 4 ohm and 8 ohm resistor are in parallel to each other. So the way I do that is I'm looking for kind of an effective resistance. So sometimes we just do REFF, effective. Okay, so that's going to be 1 over 4 plus 1 over 8 equals 1 over R effective. All right, now with that, so I go 1 over 4 plus 1 over 8, which is of course 3/8, which is 0.375. So what that means is 0.375 is equal to 1 over the effective resistance. Do not make that equal to the effective, it's 1 over that, right? So now we're going to flip both sides. So we're going to bring the, if that makes sense. If not, then multiply by REFF and then divide by the 0.375. in essence, eventually you're just going to go 1 divided by the 0.375, and we get 2.666666666. So I'm going to go ahead and just write it to 2 sig figs for now. And so I'm going to say my effective resistance of the parallel piece, so just these two together, is equal to 2.7 ohms. And what you'll notice is that that is less than either one of these, because the full current doesn't have to go through either one of those. It's going to split, and so it will be easier than it would have been if you only had one resistor there. And so the overall resistance of a parallel circuit will always be less than either one of those. It'll always be less than the lowest of those, right? So if you ever get something that's in the middle, or if it's bigger, then you know you've done something wrong. The effective resistance of a parallel circuit must be less than either one. Okay, so at this point, what I can now do is I can actually redraw my circuit. So I still have that 2 ohm resistor there, but then instead of this, I'm now going to have the effective resistance, which was 2.7, right? And so now they're in series, and because they're in series, then all I have to do is add them together, right? That's this right here. When they're in series, I just add the 2 resistances to get the total. And so I'm going to take the 2 plus the 2.7, and I get 4.7 ohms. All right? And so that would be the total resistance of that circuit right there. It's interesting how we can use larger resistances to create a smaller resistance by putting them in parallel. All right? Okay, let's try the next one. This is in our packet number 12. Okay, so it says each resistor has a resistance of 1.5 ohms. And so we're going to try to put all those together and get the total resistance of this circuit right here. Okay, so if this is 1.5 and that is 1.5, 1.5, 1.5. So the first thing I notice is that these guys right here are in parallel, right? The current comes here, it splits, it goes through those two, and then it comes back, okay? Now, to be able to do that then, we're going to use this. So we'll do 1 over 1.5 plus the second one, 1 over 1.5, and that will be equal to 1 over the effective resistance of this piece right here, right? And so I go 1 divided by 1.5 plus 1 divided by 1.5, and I get 1.33333333333, right? Now, remember, that is 1 over R effective, and so I need to do the inverse of that, so I'll do 1 over that, and I get 0.75. So the effective resistance is 0.75 ohms. All right? Now, you may notice that, yes, this is a parallel. This is also parallel, and it's identical to that one. And so if I simplify this, really what it's going to turn into is a single 0.75. So that's this piece right here. And then this piece right here would also be a 0.75 resistance. So now they're in series. And because they're in series, all I have to do is add them together there. And so I'm going to add together the 0.75 and the 0.75. And I get a total of 1.5 ohms. It seems kind of silly that we can go through all of this, and yet it's that all of that is the same as just having a single resistor. You may ask, well, why do we want to do that? Well, maybe we don't. Maybe this was just a problem created to get our brains thinking brains working. But maybe I can put different components, different loads inside of here so that they feel different potential differences, different resistances, you know. So you know, there's a variety of reasons why maybe you would do something like that. But the point is, mathematically, we're practicing using our series and parallel calculations there. All right, so that's 11 and 12. I'm going to move on now. So we're going to look at number 13. So number 13, I apologize. Your packet may, if you're in my class, the question may be missing an image. The image that is supposed to be there is this one. It's the same as question number 11. And so when you get that question, it says that there are 3 resistors with the resistance shown. We're going to use the same resistors, but we want to describe how we could get a new circuit that would have a maximum total resistance. Okay, well, hopefully by this point you're recognizing that I get the most resistance when I force every single electron, all of the current, to go through every single resistor. So that would be series, right? And so if I do that, if I go 2 ohms, and then I put the 4 ohms here, and then I put the 8 ohms after that, I put them all in series, that should give me the maximum possible resistance, right? Now in part C, it actually asks us to draw the circuit and calculate the resistance for each. So how would I describe it? I would say I would put them one right after the other in series. This is what the drawing would look like for part C. And now we're going to find the total resistance, which for a series circuit is just 2 plus 4 plus 8, which gives us 14 ohms, right? Now you'll notice that that's significantly bigger than any one of them individually. It's also bigger than what we had here. If you look back at the first example that we did, this is significantly larger than that, all right? Now, the second part of this question is, how can we rearrange these to get a minimum resistance? Okay, well, what we're going to do is we're going to put them all in parallel. Remember, if we put it in parallel, the current now splits up so that it's easier for the current to flow because I'm trying to put less through each of those resistors. And so what it would look like would simply be this. We'd go 2 ohms here. We'd go 4 ohms in the middle, and we'd go 8 ohms down there. Now, one of the things to remember is that the order of these here does not matter, okay? Often they like us to put little dots there showing that they actually come to a junction there, that they meet there. But the point is that you could have 4 to 8, 8 to 4. It doesn't matter, right? What matters is that the current's going to come here. It's going to split. It can go through any of those 3, and then it's going to go back together again and then out. So what would the total resistance be? Well, I'm going to need to use my parallel. So this time I have 3. So I'm going to go 1 over 2 plus 1 over 4 plus 1 over 8 equals 1 over the effective resistance, right? And so when I do that, then hopefully I'll get a number that's smaller than what I had before. So 1 over 2 plus 1 over 4 plus 1 over 8. And then remember, that gives you 1 over the effective resistance. So I'm going to do 1 over that, which gives me 1.14, so about 1.1 ohms. Okay, and remember what we talked about before is that the effective resistance of a parallel circuit will always be less than whatever your smallest resistor is. So you may think that by putting this in there, I'm going to cause it to increase the resistance, but it actually does the opposite, because now that parallel circuit has to be less than 2. It's always going to be less than whatever the smallest one is. By going in parallel, you are always going to decrease the resistance of the circuit. By going in series, you're always going to increase the resistance of the circuit. All right? So hopefully that's helpful in kind of visualizing some of the things that we've done, in understanding some of the things that we've done before. I want to add in one little tidbit before we go on, and that's this. If you'll remember, previously in class, we talked about this idea that power equals current times voltage. Today, we learned that V equals IR, which means if I substitute IR for V, then the power that's being lost in a resistor will be I times IR. Or in other words, I squared R. And this is in your data booklet, just like that. But you can derive it. That's where it comes from, right? But not only that, if instead of putting the V in, we put the I in. So divide by R. So V over R equals I. So we're going to use that. So we're going to go P equals, instead of I, we're going to put V over R times V. And what we get is V squared over R. So power can also equal V squared over R. So there's multiple ways to calculate the power that's being lost inside of a resistor, inside of a circuit. All right, so I wanted to make sure to introduce you to that because you're going to see that, and I don't want you to be so stuck on this that you forget that we have ways to connect that to resistance. And again, these are in your data booklet, I squared R, V squared R. If not, if you can't find it, then you can always just use the V equals IR and substitute it in. All right, so anyway, I hope that's been helpful, looking at the series, looking at the parallel, some basic circuits. If you watch the next video, we'll go into some more complicated ones and really start to answer some really good questions. All right, we'll see you next time.